All right, in part 2 of this lesson, we're going to begin looking at what a derivative is and how we would find that using in or tying in unit 1 and try to find out how we could find the slope of a tangent line or a slope at an instant. So let's just take a second. You might need to rewatch this a couple times. This could be a little tricky. But it says we're beginning with this graph y equals f of x. So this is f of x. It's just some curve. Let's begin with an arbitrary point. Let's call it c comma f of c. That's the one we have. It's already drawn for us. Let's choose another point on the curve that has a horizontal distance of change of x, or delta x, units to the right of our initial value c. All right, we're going to call this, that's going to be our point. We're going to call that x comma f of x. Place the point on your curve, preferably close to the right edge. Connect those points. What is the slope of the secant line joining those two points? All right, so that is the slope. It gives us a good average rate of change over the interval c to x, right? If I find the slope of that secant line, secant goes through 2 points, more than 1 point, it goes through that point, or goes through those 2 points, that's the average rate of change of the whole thing. On average, if I average out all these slopes of the tangent lines, it would be about whatever the slope of this is. Remember, we're trying to find the instantaneous rate of change at the point c, f of c. All right, what's the slope? Okay, so the slope, that would be our average rate of change. Same formula. It's f of x minus f of c over x minus c. And this distance that we had right here was delta x. Just whatever this is. Now, technically, this should be x plus c. I don't want to get into that too much. This distance right here, that's just the change in x, but it's not x. It's just the change in c to x. All right, so anyways, there's our little slope. That would find it. Cool. No, now just for kicks, let's let our second x value, just another one, I'm still going to call it x, but it's a different x. We're going to have that a little bit closer to the original x value of c, reposition the point so that it's about half as close to c f of c. So, okay, that's good enough. Is it about half? Sure. Is it exactly half? I don't know. And now we connect the 2 points. Do we still see a secant line? Well, yeah, it looks like it crosses through and it's not tangent, not just 1 point. So I'm going to say yes, I still see a secant line. Is there any difference in the way we calculate the slope? No. It would still be f of x minus f of c over x minus c. Even though the x's are different, right? But notice the x is a little bit closer, so that change in x is a little bit smaller. All right, where did this line come from? Okay, since we're having such a blast moving our second x closer to c, let's move the x value so it almost touches c. Reposition f of x so that it's right next to our original point. Okay, I'm going to zoom in as close as I can. There it is. There's my point. That's the point, x f of x. Do we still see a secant line? Yes, but it's almost tangent. Because it's super close, right? Almost tangent. I didn't connect the 2 points yet. So I'll connect the 2 points. I mean, that's terrible. Well, I guess not terrible, but I want to look kind of tangentish. So it's a secant line technically, but it's still really close. It's almost a tangent line. So how can we perceive the slope now using a very important concept from Unit 1? All right, so the slope is let me give myself a little room. F of x minus f of c over x minus c, right? What is happening to the distance between x and c? What's happening to x each time that we've gone a little bit closer. It's it's the x number and the c number are almost the same thing, right? So I'm going to say the limit, and you might have cheated and looked down here. You wouldn't do that. The limit as x approaches c of this is going to equal the slope of the tangent line, which is going to wind up being, we'll talk about this probably more in the next lesson, the instantaneous rate of change, which is also going to be our definition of a derivative. So that's our first major calculus idea. This idea of the limit as the x numbers are approaching c. So as those 2 points, they're a secant line, but as x approaches c, it becomes a tangent line. And if I find the limit of this function, that'll tell me the slope at the instant when x is c. And that's huge. And we're going to be talking about this for a while. All right, so the definition of a tangent line with slope m. So the slope of the tangent line, if f is defined on the open interval containing c, so the open interval, I don't know why you wrote that. You don't even know that now. Containing c, and that if the limit of that is, well, what we just said, right? The limit as x approaches c, and if it exists, then the line passing through the point c, f of c with slope m is the tangent line to the graph of f at that point. Now that might be something you need to reread a couple times. I read it through really quick and I kind of mumbled my way through it. But there's our definition of a tangent line, which is going to also be a fancy definition. Not that fancy, I think it's fancy. Fancy definition of a derivative. Exciting stuff. All right, 3 more examples and we're done. All right, using the limit process to compute derivatives. Find the instant... I think I didn't write a certain thing. Okay, prime notation. It's not on this notes. It's on your printout. Prime notation, that's read f prime of c. So f prime of c is the limit as x approaches c. So that's our derivative, right? That's a lot easier to say. Derivative notation. We'll talk about more of this next lesson. But f prime of c is the derivative of the function at the point when x is c. So at an instant. That's prime notation. So find the instantaneous rate of change of the f function at x equals 3. So it matters where. It matters if we're doing this at x equals 3. If we're doing this at x equals 2, we would get a different derivative. We would get a different slope of a tangent line. All right, so how do we do this? F prime of 3 is equal to the limit as x approaches 3 of f of x minus f of 3 over x minus 3. Now, some of you are like, oh, Mr. Walbrand, I know this already. I know what the derivative is. Just hang through it. I want you to see how this limit idea ties together. Some of y'all can look at this and know what the derivative is right away. And that is awesome. Let's talk about that just to kind of cheat. All right, so this function is just a linear equation. Y equals mx plus b, right? Mx plus b. So, oh my goodness, that's not it. -1 y-intercept. We're going to call that slope of 4. What is the slope at any point on that graph? The slope of any point is going to be 4. We already know that. But let's see how this limit definition ties together, because it does show up on the AP exam sometimes, and we got to see how it works. All right, so f of x. F of x, so I'm going to keep my limit notation coming over. The f of x is 4x minus 1 minus f of 3. Well, what do I get when I plug in 3? 3 times 4 is 12, minus 1 is 11 over x minus 3. Okay, let's clean this up. Now, don't write 4x minus 12. Oops. That's technically not right. We need to keep that limit notation coming over. So 4x minus 12 over x minus 3. What's this limit? This is a good little practice from Unit 1. We're going to do some factoring. This is equal to the limit as x approaches 3. Factor out of 4. Oh my goodness. Okay, I'm probably the only one getting this excited. Those cancel, and my answer is 4. That's what we just said it was going to be. Some of y'all even know the power rule, and you know the limit was going to be 4, or the derivative was going to be 4. Okay, we're just seeing this all ties together. All right, 2 more examples. Next page, okay. Given the g function, okay, this is x squared minus 2x plus 1. It's a quadratic, so the slope of the tangent line is not going to be the same everywhere. Find g prime of 4 and write the equation of the tangent line to g of x at x equals 4. Okay, so this is something that's going to come up over and over and over and over and over. So if you don't get it right away, we will do this probably 100 more times. And you'll like, okay, how did I ever struggle with this? But that's part of learning. First time you see stuff, it's kind of weird. Then it gets better. All right, find g prime of 4. Okay, step 1, find that. Then we also have to write the equation. So it's two parts. This is a good little FRQ practice because they often ask more than one question at a time, and make sure you're answering both questions. So first of all, g prime of 4. Well, g prime of 4, if you know the power rule, it's going to be pretty fast once we know the derivatives and get even better with our little tricks. But right now we're going to use the limit definition. Limit as x approaches 4 of the g function. Okay, it's because it's g of x minus g of 4, right? So we're just going to write this out. Minus whatever g of 4 is. Okay, g of 4, I'm going to plug 4 in for the x's, right? So 16 minus 8 plus 1, is that 9? I think that's 9. Wait, that sounds right. Okay, 4, 16, minus 8. 4 times 4 is 16, minus 8 is 16, plus 1. Why is it so hard for me for some reason? Yeah, I think it's 9. All right. Don't know what's happening. Over x minus 4. All right, so need to make the top look better. The limit as x approaches 4 of x squared minus 2x minus 8 over x minus 4. We need to do some factoring. Oh, no, go away. Okay, equals the limit as x approaches 4 back to the top. Oh, that looks the same. So this time we have the limit as x approaches 4 of a function. Okay, last time it just got a number, right? Because that was a linear function and the slope of a tangent line is the same everywhere. But for a quadratic, it changes based on what your x is. So now I plug in 4 and I would get 6. So g prime of 4 is equal to 6. Step 1 done. Write the equation of a tangent line. So we're going to use our point slope form. To write an equation of a line, you would need the point slope form, which was y minus y1 equals mx minus x1. That's where you have a point. The point you have is x1, y1, and the slope is m, right? That's our g prime of 4. But we are going to, I want you to put this on your memory sheet. I'm going to write it like this. It's just faster. That gives us some point slope form. So all we did here was add the y1 to both sides. That's just, I think, better, easier. All right, so the slope of our tangent line is y equals m. That's the slope that we just found, g prime of 4, right? X minus x1. Okay, well, we need the point at 4. We needed to know what is the point of the g function when x is 4. We found that, right? G of 4 was equal to 9. So it's going to be x minus 4 plus 9. And there it is. Using that point slope form. And I can leave it just like this. I could distribute the 6 and clean it up a little better, make it look like just like a mx plus b form, but we don't need to do that. But just in case you want to, distribute the 6x minus 24 plus 9, y equals 6x. Oh gosh, I have to add negative 24 plus 9. I don't want to do that. Just leave it. Don't make mistakes. It's the same thing. All right, last one. I want you to pause the video, do this one on your own, see if you can come up with it. This is a AP style question on the multiple choice. So once you've paused it and done it, you're back. It says if f is a function for which the limit as x approaches negative 2 of f of x minus f of negative 2 over x plus 2 is equal to 0, then which statement must be true? So if it could be false, it's not it. It has to be true. X equals negative 2 is a vertical asymptote. Okay, I think the idea here is if that was infinity, right? If the limit as x approaches negative 2, if we got this was infinity, it'd be a vertical asymptote. That's something we talked about in Unit 1. But that's not happening, right? So does that have to be true? No. That's not it. The function f is continuous at x equals 2. X equals 2. Oh, wait, let me back up. X equals 2, I don't really know what's even happening there. Who cares about x equals 2? Can I say it as x equals 2? I could say it's... I don't know if it's defined. I don't know what f of 2 is. Do you know what f of 2 is? Do you know the limit as x approaches 2 from the left is equal to the limit as x approaches 2 from the right is equal to f of 2? You don't know any of that, so no, that doesn't have to be true. It could be true. I don't know. It could be true, but I don't know for a fact. The derivative of f at x equals negative 2 exists. Huh. Maybe. Let's see. Yeah, that feels right. We just talked about derivatives, right? And that looks like it. F is not defined at x equals negative 2. That could be true. If I have the limit as x equals negative 2 is 0, it doesn't mean it's defined there, but it could be defined there. So it couldn't have to be true. So it's C on process of elimination. But what this is saying is this is the fancy limit definition of a derivative. Saying the limit as x approaches negative 2, that's our C number. If it's given a number, then we know it exists. And I actually know that the derivative is 0, but it just says the derivative exists. So it's even better. It's even more vague. I know the derivative, at x equals negative 2 is 0. All right, so that would be C. All right, as always, if you have any questions, next time we see each other in class, just please ask.